Okay, welcome to Robotics 1. In today's class, I'm going to talk about root locus. Now, what do we mean by root locus? Locus is the trace, and root is nothing but the location of the poles. So consider a feedback system. And for the sake of discussion, what I'm going to show is a very simple feedback system. So this is G of S. Then you have a summing junction. And then what we have is we have a feedback, which is H of S. And it's a negative feedback. So you have positive here, negative here. This is output. This is input, which is U, and this is output. Now, overall transfer function for this system, the transfer function for this system is given as GS divided by 1 plus GS HS. This is what we derived in last class. Now, what I want you to visualize that I'm going to add a gain term here. So I'm going to add a gain. And what do I mean by gain? Gain means nothing but an amplifier. So whatever error I'm going to get, I'm going to amplify that by a gain K. So this is gain K. Now, please understand that the poles of the original system are governed by this equation. So this determines poles of the transfer function. Now, once I add this gain, my transfer function gets changed. So the transfer function with gain K becomes transfer function is equal to K times G of S. Just visualize that initially that which was G of S now has become K plus G of S. So you can think about like now your block is K times G of S. So now this block has become 1 plus K times G of S H of S. Now, for the sake of discussion, I'm going to assume unity feedback. Unity feedback. What do I mean by unity feedback? Means H of S is equal to 1. That's what it means by unity feedback. So with unity feedback, my transfer function now is K GS divided by 1 plus K G of S. Now, here is the idea. What I want to know is, I want to find out, here is the question. So, how do poles change as K is changed from 0 to infinity? So this is the question that I want to answer. So if I have an amplifier, if I have a gain in the system, And if I change the gain, what is the effect of that gain on the poles of the system? So what does that gain do? Does it make system unstable? Does it make that system stable? Does it control the response? What exactly that gain does? And this answer to this question is nothing but root locus. So root locus means how do the roots change, or how do the poles of the closed loop transfer function? And please note, this is the closed loop transfer function. So this is the closed loop transfer function. How do the poles of closed loop transfer function change depending upon the change in the gain? And that is all there to it. So what I'm going to do is I'm going to take a simple Matlab example, and then we will show how to plot the root locus. Now, what was the purpose of root locus? And at one time when the signals were analog, uh, there used to be a lot of operational amplifiers in the control systems. And the idea would be, how do you tune these amplifiers so that the system response is what we need? So nowadays we can use Matlab, but before Matlab, people used to do hand calculations, and there are some simple rules that allow us to calculate and plot root locus. So, and they used to plot root locus and then find out the approximate gains so that the system response is what is required. So let me give you this question. So question is, plot root locus of following transfer function. So the transfer function g of s is given as s plus 7 divided by s plus 5 s plus 15 s plus 20. So this is the transfer function, and what we want to do is we want to find out the root locus. Now the question is, what do we do once the root locus is found out? So what I want to do is I want to find the value of gain, find the gain k, find the gain k such that, find the gain k such that overshoot is less than 5% and rise time is 1 second. So once the root locus is plotted, what we want to do is we want to find out the gain value in such a way that the overshoot is less than 5% and the rise time is equal to 1 second. Now, there are two ways to solve this problem. One is using the Matlab, and other one is using the hand calculations and the notes that we discussed in last class. So for overshoot to be less than 5%, for overshoot to be less than 5%, damping ratio has to be greater than 0.7. And if you recollect the table that we discussed in last class, that table will give you this information. So there is certain value of damping ratio for certain value of overshoot, and for rise time is equal to 1 second. The natural frequency omega n, which is the natural frequency, should be greater than 1.8. Now, what we are going to do is we are going to plot the root locus, and on the root locus, we are going to find the value of gain in such a way that these two conditions are satisfied. And later, what we are going to do is we are going to look at the closed loop and open loop response, and then later we'll see the closed loop and open loop response. Now, before I start working out the problem, I want you to note that this is an open loop transfer function. So this is an open loop transfer function. There is no control, there is no closed loop on this. What we are going to do is we are going to add a gain. So right now, and this setup is very important. Right now, this is for the system we have S plus 7 divided by S plus 5, S plus 15, and S plus 20. This is how the system is. And clearly, when we look at the open loop response, we will realize that the system response is not what we want. So what I'm going to do is I'm going to add a feedback, a unity feedback. So step 1 is to add unity feedback. And step 2 is to add a gain. So add a gain. And then add gain. Now this system has become closed loop. But at this point, the value of K is not known. We do not know what is the value of K. We know that initially the system was open loop. We made that system closed loop. We added the gain. But what we want to do is we want to select the gain in such a way that these two requirements are satisfied. And that's what I'm going to do. So if you have your Matlab open, I want you to start Matlab, and then I will show you how this problem can be solved. Before I begin, any questions? Is setup clear to everyone? We have an open loop transfer function. What we want to do is we want to convert that open loop system into a closed loop system and find the gain. Root locus is found out for closed loop systems. You cannot find out root locus for open loop systems. Root locus is found for closed loop systems. What is a finite pole? Okay. So if they ask you to find root locus, you will convert an open loop system into a closed loop system. However, I just want to be very clear. The way Matlab works, Matlab can take an open loop transfer function, convert it into closed loop transfer function, and find the root locus. So when we are going to solve inside Matlab, Matlab can work with open loop transfer function. So I have another question. What is a finite pole? So finite pole, my understanding is, which is at a finite location, which means it has a real part and it has an imaginary part. And if you have an infinite pole, which means the pole can be located at infinity, and I can totally see a condition when the pole can be at infinity is you have in the denominator you have a term something like 1 by s, and that could give rise to a pole at infinity. Okay, now I'm going to switch to Matlab, and this exercise is very important, so please pay attention. Now you should be seeing my Matlab screen. So first and foremost, I need to create a transfer function. So I'm going to start with something like this. So line number 1 is defining an S variable, and I will post this in my chat window. For some reason, chat window has disappeared. Okay. Okay. So in the chat window, you should be seeing the code. Now, once you run this code, what it will do is it will plot the root locus. And I will show you, I will share my root locus. So are you able to see the root locus? This is how the root locus is gonna look like. And what I want to do is I want to spend some time and show you what is on the root locus. First thing I want you to observe that there are x's. So here is one x, here is another x, here is one more x, here is one more x. So these are the poles of the open loop system. I want you for a second look at the open loop transfer function. Denominator of open loop transfer function is of the form s multiplied by s plus 5 multiplied by s plus 15 multiplied by s plus 20. So I want you to note that this value is s is equal to minus 20. This is the pole of the open loop transfer function. So there is an X sign here, there is an X sign here, there is an X sign here, and there is an X sign over here. So, and I'm gonna move this little bit so you understand. So please note the X's indicate open loop open loop poles. And O indicate open loop zeros. So if you look at this O, this is an open loop zeros. And please note that this open loop 0 is at location s is equal to -7. So now what we have is we have this root locus. So now what I'm going to do is I'm going to show you how does this. So what I want to do now is check this out. So as you travel on the root locus, I want you to observe as I'm traveling on the root locus, the gain value is changing, and this is the value of k. So what it does, it starts with the gain value of 0. Can you see that I am at the gain 0? And now I'm going to drag this. And you will see the gain value keeps on changing. So this is how my poles change as I travel on the root locus, and corresponding gain values also change. So this is what it means by plotting the root locus. Now I need to go to the next part, and so I want to find out that what is the value of gain k if my overshoot is less than 5%. So I'm going to go back to Matlab. So here is the question. What is the value of gain when my overshoot is less than 5% and my rise time is equal to 1? And condition for overshoot to be less than 5% is the damping ratio should be greater than 0.7. So condition for overshoot to be less than 5% is that damping ratio should be greater than 0.7 and the natural frequency should be greater than 1.8. So what I'm going to do now is I'm going to run the entire code again, and now I will show you the plot I got. I will show you the plot that I got. Now you will see that interestingly, I have sort of a semicircle, and this semicircle indicates the frequency of 1.8. So this is omega n is 1.8. And these two dotted lines, they indicate the lines corresponding to damping of 0.7. So what I want to do is, now I want to select the value of the gain, so that my poles are within these lines of damping and outside this circle. And I just want to wait here for a second and just make sure that everyone got the same figure that I have. Everyone got the same figure that I have? Okay. Now before you do anything, just see what I'm gonna do. These crosses, these x's are the open loop pole. These are the original poles of the open loop system. Now what I'm gonna do is I'm gonna click here, And can you see at this location, can you see my damping is 1, but my frequency is 0.446. And I want my frequency to be greater than 1.8. So I want you to click on any point inside that circle, and you will notice that your overshoot will be less than it is 0% here. It will be less than 5%, but your frequency is going to be less than 1.8. But you want your frequency to be greater than 1.8. Now I want you to click here. Now here you will observe that you have gain of 4.6 10 to the power 3. Your frequency is 12.1, which means your frequency is greater than 1.8. But please observe your overshoot is about 68%, which means clearly that if you choose these 2 points that I have chosen, the system performance, the specifications of system performance are not satisfied. So what I'm going to do is, I am going to drag this, observe the frequency ingredients keeps on changing. And now I go here. And can you see when my gain is 279, my overshoot is 0% and my frequency is 1.97. So at this gain value, a gain of 279, my both the conditions are satisfied. So that is what it means when you try to solve the system using this. Okay, before I proceed further, everyone understood? Any questions here? Now, next part is important, and I'm going to go back to Matlab. So what I want to do now is I want to look at the step response of open loop system. Now my open loop system is this. So this is open loop system. So I'm going to type step SYS and see what happens. Step SYS, evaluate the selection, and then you will observe, wow, the step response is, it's like a straight line. It goes all the way up. It does not dampen out. Now what I'm going to do is I'm going to create a closed loop system, and this is very important. So creating a closed loop system. So how do I create a closed loop system? I want to specify the value of gain, and our gain was 269. Okay, my gain was 269, and I'm gonna create SYS underscore CL is equal to feedback K multiplied by SYS, that was the open loop, and I had a unity feedback. So I would just say K SYS 1. So sys underscore cl, I made a mistake. This is not fed back, it is feedback. 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 And last but not least is I'm gonna do step response of a closed loop system, sys underscore cl, and I want you to run this code. And when you run this code, it will generate a plot. And I'm gonna show you that plot. Do you get the plot that I have? Do you get the similar plot? So now, if you noticed, earlier step response was a straight line. It went from here all the way to 25. It was a straight line. It didn't converge. It didn't have a steady state value. But as soon as I converted an open loop system into a closed loop system by adding a unity feedback and a gain, now my system response has kind of got bounded. I can right click and then I can add the characteristics. So I would say rise time, then I would say settling time, I would say peak response, and you will notice, oh, my rise time unfortunately is 1.37. So I need to increase the gain a little bit further. So you can try with gain k is equal to 350. So run this code. So run this code. And see what happens now. Let's go back to the Matlab. And I'm going to change the value of gain to be 350. And then evaluate selection. Then share my screen. And then if you right click, add the characteristics, you say rise time. Wow, rise time is now 0.986. Settling time, right click, peak response. And this is how the system can be controlled. So what we did is we added a gain, and with that gain, the system is now controlled. Any questions here? Now I want to show you something else. This is another important tool. You can do the exact same thing with something called as the Control System Designer. So this is an app, and this Control System Designer will need the open loop system. So the command for that is Control System Designer. In the parentheses, we will add our system, SYS. Control system, so this is small, C is small. So copy, paste, and evaluate selection. And once the MATLAB runs, something interesting is going to happen. and I will show it to you in just a second. So what you're going to have is you're going to have all the information about this system. So you will have body plot, you will have root locus, you will have step response. You will have body plot, you have root locus, and you will have step response. I'm going to wait for a minute and see everyone got this control system designer. Everyone got this plot? I mean, this these three plots. Okay. Now I want you to highlight C. C is nothing but, and you will see that in the preview, is something called as a compensator, or this is nothing but the value of the gain. We don't need body plot. So what I'm going to do is I'm just going to look at root locus for the time being. So I have a root locus and I have a step response in the same plot, and that is very nice. This root locus is similar to the earlier root locus that we had. Now here is what I'm going to do interactively. So check this out. This is a pole. This is a pole. This is a pole. And this is a pole. Remember, our system has 4 poles. The poles are S is equal to 0, S is equal to -5, S is equal to -15, and S is equal to -20. So these poles are all highlighted. Now I am going to drag the pole, and I want you to observe what happens to the step response. Can you see that as I start dragging the pole, my step response changes? And here I can actually add the characteristics. Now watch what happens. So what I'm going to do is I'm going to interactively drag the pole, and you will see that my settling time, my rise time, my steady state, all these values, they change during runtime. And I want you to observe the gain value over here. C is the value of the gain. So this way I can interactively achieve the performance specifications. So with this, I can add the performance specifications directly onto the root locus. There is one thing I want to show you, but before I do that, everyone, were you able to move the pole and see the changes in the step response and see that the gain got changed? Any questions here? Now what you can do is you can right click on the root locus editor, and in the root locus editor, once you right click, you will go to the design requirements, right click 1, 2, 3, 4, 5, 6. Sixth row is the design requirement. Click on the new design requirement, and then it will open up. I'll show you what it will open up. So it will open up something like small dialog box. Everyone able to get this dialog box? So you will have to right click on the root locus editor, go to the characteristics, and then click on new characteristics, or new requirement, and that will give you the requirements. Just make sure that you have it. And here you can actually add percentage overshoot. Our percentage overshoot should be less than 5%. My percentage overshoot is less than 5%. And as soon as I added my percentage overshoot less than 5%, you will notice something interesting has happened. Can you see that this root locus, all of a sudden, certain part became yellow and certain part became white. So what that tells me is now I can choose the values that are outside the yellow region. So what I would do is I want to choose the values that are outside the yellow region, and that will meet the performance specifications that I need. So that's what this means. So check this out. What I'm going to do is I'm going to change these values. And please note, as soon as for some reason, if I go outside, if I am in the yellow region, my performance specifications are not met. So in this particular case, as you can clearly see, right click, design requirements, characteristics, new, you can actually add the design requirements on the step response. So I'm going to show you. Rise time is 1 second. Percentage overshoot is 5%. And then it tells me that I am way outside my design requirements. So right click on the step response. Once again, right click on the step response. Right click on the step response, and then you can add the design requirements. Now this entire system design can be done in one shot. So now as soon as you are in the white region, guess what? The system requirements are met. As soon as you cross that black line, the system requirements are not met. So this is how you can tune, change the gain, and the system response can be controlled. I'm gonna go back to the whiteboard. So we looked at how to solve root locus problem. Now the next natural extension of this problem is how do we do PID control? Now first and foremost, let me tell you what do I mean by a PID control. So what is a PID control? PID stands for proportional integral derivative control. So what that means is, compared to root locus, in the root locus, we just had one constant. So this is how we started. I had a system. Okay, I had a system. And this was the open loop system. there was no closed loop. So in root locus, we added one gain in the closed loop. Now what I'm going to do is I'm going to add a block. I'm going to call this a controller block or the PID block. I'm going to add a PID block and I will have a feedback. And for the sake of simplicity, I'm going to assume a unity feedback. So this is negative, this is positive, and this is how the system goes. So here what I have is I have Y and I have U. And here is the error. Here is the error. This error gets fed to the PID block. And how does this PID block look like? This PID block, sometimes called as C of S, this is actually a controller. I'm going to just write its definition in time domain. This is going to have a gain multiplied by the value of the error. So what it will do is it will take the error and multiply that. Please note, this is what we did in root locus. This is what we did in root locus. But in addition to that, I'm going to add another gain, which is Ki, that is dependent on the integral of the error. And I'm going to add one more term, which depends upon the derivative of the error. Det by dt. So this is called as proportional because this gain Kp is proportional to error. This gain Ki is called integral error or integral gain. And this is called as derivative. So I have proportional, I have integral, and I have derivative. Now, what does this mean? So I just want to start with what is the physical interpretation of E. ET is nothing but error between output and input. Now, this error signal is actually fed to PID. So this is fed to PID block. And some of you may ask me, what is the physical interpretation of this? Now, PID block can be interpreted as a control system. Say for an example, you could have an actuator and that actuator moves depending upon the voltage that is supplied. And if you have certain error, then you would add an amplifier in your control algorithm on a microcontroller like Arduino. You would implement a software algorithm saying that as soon as you have a difference between the output and input, you increase the voltage by 10 times. So as soon as you get error of 1 unit, the voltage to the actuator is increased by 10 volts. Now, next thing is you have something called as the integral error. This integral error is sort of it's accumulating the error as the time goes on. And Kd is the derivative gain. So it is actually differentiating the error. So you have Kp, Ki, and Kd. And these three terms, they work together and the input is dependent on the not only the error, but the rate of change of error and how much error has accumulated from the beginning. So let me write this once again. U of t is equal to kp e of t plus ki integral et dt plus kp det by dt. Now what I'm going to do is I'm going to take the Laplace transform of this. And then once I take the Laplace transform, I have an equation kp integral, Laplace transform of integral is 1 by s. Laplace transform of derivative is s. So now I have this transfer function of PID, and this transfer function of PID, this is KD, transfer function of PID can be written as KD s square plus Ki plus Kp s divided by s. This is the transfer function of PID. This is called as transfer function of PID. Now, I just want to tell you what this Kp, Kd, and Ki does. So, whenever you have a Kp term sort of gives a push, which means it sort of forces the output to be close to input. It tries to push the output close to input. It reduces but does not eliminate steady state error. So it reduces but not eliminate steady state error. So with the Kp, you can actually increase, if you can increase the value of Kp, that will actually make the output go very close to input, but not at the exact same location. That's exactly what happens when you try to design the system, control system using root locus technique. So if you add additional term, which is Ki, if you add an integral term, Ki, what this integral term does, it helps to reduce steady state error. So it helps to reduce the steady state error. Now, what happens is if you add KD, this KD sort of anticipates what's going on, because think about it. KD depends upon the derivative. Derivative is nothing but sort of the slope. So it tells us whether the error is increasing or whether the error is decreasing. So basically, this actually sort of anticipates the error. And this is something that is important. So it is sort of an anticipatory term, anticipation. But it does not have no effect on steady state. But if we add an integral term, the only problem with integrator term is something like system becomes sluggish response. So ideally, you want to tweak and tune all these systems in such a way that the system response is the way we want. So I want to take a minute here and before I solve a problem, I just want you to understand that there is a KP, KI, and KD type of term in the control system. And depending upon what you do, the various gains change the behavior of the system. And now I'm going to take an example. So imagine, let me set up the problem, and then I will solve this problem with Matlab. So consider that I have a spring mass damper system. Now I have a spring mass damper system. This is the mass, this is the damping, this is the stiffness. M is mass, B damping, and K stiffness. Now we discussed the transfer function of this system, and I'm just going to go ahead and write the transfer function down. This transfer function is something like ms square cs plus k. Yeah, I would answer that question in just a second. So for an example, if you have a robot joint, if you have a motor and you want to control the motor, then you want motor to go to a certain point in time. Then you tune the gains so that the motor goes to that appropriate point. Now, I would be honest with you, unless you play with the system on a hardware, this concept may not be clear. So in robotics 1, in today's class, I'm gonna give you theoretical background, but when you come back for robotics 2, I'm gonna start with KP, KI, and KD, the PID control, and then there will be a lab wherein you will control the motor. You will implement a closed loop control of a motor, and that will make this concept very clear. So there is a practical part to it, but that we will be doing in the first week or the second week of robotics 2. Does that answer your question, Tyler? Right, so you can think about it, but nowadays we don't use op-amps. We actually use the microcontrollers like Arduino, and in microcontroller, we physically set up the value and change the value of the pulse width modulation or the voltage or something like that. So it's actually, so we don't in earlier days, there used to be knobs for KP, KI, KD. You will tune those, but nowadays we implement those, especially we implement those in robots using a microcontroller. But we will work on those in robotics 2. Robotics 2 starts with PID control. Okay, so what I'm going to do is, in today's lesson, I'm just going to give you an example. So mass is equal to 1 kg, then B is equal to 10 Newton second per meter, K is equal to 20 Newtons per meter, and I'm going to say external force F is equal to 1. Now what I want to do is, I want to see how Kp, Ki, and Kd affect the behavior. specifically, I am interested in looking at what it does to rise time, what it does to overshoot, and what it does to steady state error. So what I'm going to do is in next part, I am going to go to Matlab, and bear with me for a second as I switch my screen to Matlab. So when I go to Matlab, so you should be seeing my Matlab window. First, I'm gonna create a transfer function. So I created this transfer function. And I will go ahead and type this into the chat window. So this is the transfer function. And I want you to see how does the spring mass system behave to a step response. And you will notice the step response of the system looks something like this. Then what I'm going to do is I'm going to add the controls, PID controls. So next part is I'm going to add a KP term. So KP and this is the code. So what I have done, if you recollect, this is exactly similar to what we did before, except I've used the command PIDKP that generates the transfer function. And earlier I just had a gain. Now I have C times P. So I have PID multiplied by the plant transfer function, and I have a unity feedback. So I right click, select, run, and then I want you to see how does my response look like. Can you see my step response now got sort of oscillatory and bounded? So initially it was not like this. And again, now I'm meeting the initial specifications. On here, I can select peak time. I can select settling time. I can select rise time. And then you will see my rise time is 0.07 seconds. My overshoot is 40%. That's not good, but we'll try to reduce that with I and D control. Then my settling time is 0.772 seconds. Now what I'm going to do is I'm going to add the D control. So KPKD and now you can actually highlight this, evaluate, and then if you see the plot, this plot is significantly different than the previous plot. Right click, characteristics, look at the peak time, settling time, rise time, and steady state. So you can see the system response has improved significantly. Now I'm going to add KP, KI type of term. So KP and KI. KP and KI, and highlight, evaluate, and I will show you how it looks like. And now you will see that there is no oscillation at all. So system, there is no overshoot. Right click, characteristics, peak time, settling time, rise time. Yeah, I just changed value of KP. To be honest with you, I haven't told you how to tune KP, KI, and KD. But bear with me just for a second. The last part is KP, KI, KD. So this is what you should be seeing. And then your step response would look much, much cleaner when you have KP, KI, and KD. So you can see the system is sort of goes up. And so how do you tune the KP, KI, and KD? Now I'm gonna give you some guidelines. So, and we will talk about these in detail. So first we add a proportional control. Proportional control will control the rise time. Then we add a derivative control. Derivative control will minimize or reduce the overshoot. And then we add an integral control that will reduce the steady state error. Once again, the steps are: first, add the proportional input, control the rise time, then add the derivative input to reduce the overshoot, and then add an integral control to reduce the steady state error. Now, one thing I just want to show you is Matlab will help you tune PID gains automatically. And there is a command which is called as PID Tuner. So what you can do is, it's like PID Tuner. And then it needs open loop system. So this is the command PID Tuner. And once you click, the PID Tuner will open. And I will show you in just a second how that PID Tuner looks like. So you should be seeing the PID Tuner. It says type P. There are multiple options. You can click PI, PI, PD, PID. Then if I were to say PID, then I can actually move the response time. I can move the transient behavior. I can actually click. I can actually show what type of plot it is. I can add different characteristics. And now I can do these modifications, these changes in the runtime. So I can move them around, and then it will actually help me to tune the PID control in runtime. If And then if you want to show the parameters, just click on show the parameters, and it will give you the value of not only KP, KI, KD, it will give you rise time, settling time, percentage overshoot, peak, phase margin, gain margin, and so on. So with this, you should be able to tune the PID controls interactively. There is another way of doing it, and we will talk about it in next in robotics too. You can actually have the PID control tool automatically tune the PID gains. So there is a command that would allow you to gain the PID controls automatically. But this with this interactive tool, you should be able to do the PID control. I'm gonna stop here, and I would be happy to answer any questions you may have.